How did a machine designed to stabilize power become powerful enough to tear a factory apart from the inside? If you are drawn to uncovering how overlooked engineering decisions reshape entire industries, subscribe and stay with this investigation as we trace how stored motion turned into systemic risk. Across the industrial world in the late 1800s, factory owners faced a simple but stubborn problem: how to deliver steady, reliable power to hundreds of machines from a single steam engine. Steam engines, especially the piston-driven types common in textile and steel mills, produced energy in sharp, uneven bursts. Each stroke threatened to snap threads, jam looms, or throw off delicate timing. To keep production lines moving smoothly, engineers needed a way to absorb these pulses and release energy steadily, something that could act as both shock absorber and battery. The answer was mass and inertia. By mounting a flywheel, sometimes weighing 20, 60, or even 100 tons, at the center of the engine house, factories could store rotational energy in a spinning rim. The heavier and larger the wheel, the more energy it could hold, and the more effectively it could flatten out the irregular surges from the steam engine. In period surveys, mills across New England and Lancashire routinely reported flywheels of 20 to 100 tons, with diameters stretching past 30 feet. These wheels were not hidden away. They sat at the literal heart of the factory, sunk into deep pits beneath brick engine rooms, their motion transmitted through belts and line shafts to every floor and workshop. This centralization was not just an economic choice, it was an economic calculation. One giant flywheel, driven by a single powerful engine, could supply the entire complex. Owners could cut fuel waste, reduce the number of skilled operators, and keep every loom and lathe running at a constant speed. The business case was clear. More mass meant greater stability, higher output, and lower costs per unit of power delivered. The flywheel's inertia did the work of 1,000 hands, smoothing out the wild heartbeats of the engine and allowing factories to scale up like never before. But the logic that made these wheels so attractive also set up a hidden contradiction. Every increase in rim mass and diameter multiplied the amount of energy stored in the system. At 60 revolutions per minute, a 30-foot flywheel could spin its rim at over 100 miles per hour, holding enough kinetic energy to rival a small explosion. Yet the material limits of cast iron, brittle and prone to hidden flaws, remained fixed. The drive for efficiency and centralization pushed engineers to build ever larger and heavier wheels, even as the stresses at the rim quietly climbed toward the breaking point. In the pursuit of smooth, reliable power, factories had concentrated not just energy, but risk at their core. The power of a spinning flywheel is not just a matter of mass or size, it is written into the steel and cast iron itself. At the heart of every industrial flywheel is a simple relationship: the stored energy scales with mass, the square of the radius, and the square of the rotational speed. That means every extra foot of diameter, every additional ton at the rim, multiplies the stored energy far more than a casual glance would suggest. But the real hazard lies in how stress builds as the wheel spins faster. The tension in the rim, what engineers call hoop stress, does not just rise with speed, it rises with the square of the speed. A flywheel running at 60 revolutions per minute already has its rim moving at over 100 miles per hour if the diameter is 30 feet. If the speed creeps up by just 10%, the stress does not climb by 10%, it jumps by more than 20%. That is because the forces pulling the rim apart scale as rotational speed squared, not just rotational speed. Cast iron, the material of choice for most 19th century flywheels, brought its own limits to the table. In compression, cast iron is strong, but in tension, it is brittle, failing at pressures below 20,000 pounds per square inch. That is the ceiling. In practice, flaws from casting, tiny gaps, inclusions, or seams could lower the breaking point even further. Engineers of the era knew the numbers, but the drive for more stable power and greater output often pushed wheels closer to their red line than anyone admitted. Segmented rims bolted together for easier casting, and transport introduced new stress points. Every bolt hole, every seam became a place where fatigue could start, spreading micro cracks with each revolution. Weeks of continuous spinning meant millions of stress cycles, each one a silent test of the metal's integrity. The contradiction was stark. The same inertia that made these wheels so valuable for smoothing power also made them sensitive to overspeed. A brief surge, a belt grabbing after slipping, a governor sticking, could push the rim past the material's limits in seconds. Once that threshold was crossed, the stored energy had nowhere to go but out, transforming a stabilizer into a source of destruction. What began as a calculation on paper became a question of survival for everyone in the building. Inside the foundries of the industrial age, casting a single 30-foot iron ring was out of reach. Instead, flywheel rims were built as a circle of bolted segments, each one poured, cooled, and machined before being fastened together on the engine's hub. This method made transport and assembly possible, but every seam and bolt hole carved a hidden weakness into the wheel's structure. At these joints, the iron's grain was interrupted, creating natural starting points for cracks. The bolts themselves, meant to hold the segments tight, focused stress into small pockets around each hole. Once the factory's engine started, the flywheel rarely stopped. Weeks or even months of continuous spinning meant millions of cycles, each one stretching and relaxing the rim as power demands shifted across the line shafts. Even at steady speed, the iron was pulled outward by centrifugal force, loading the rim at every revolution. The real danger, though, came from the rhythm of industrial life, belts tightening and loosening, machines starting and stopping, brief surges of overspeed when a governor stuck or a belt suddenly grabbed. Each of these events sent a pulse of extra tension through the rim. Microscopic flaws, air pockets, inclusions, or rough patches from the casting process could lie dormant for years, but under the relentless cycle of stress, they began to grow. A crack would start at the edge of a bolt hole or along a seam, invisible to the naked eye. With each revolution, it crept a little farther, following the path of least resistance through the brittle iron. No amount of surface inspection or hammer testing could spot these internal failures in time. By the time a crack was big enough to matter, it was already too late. The cracks had been growing unseen. The seeds of disaster were planted not by a single mistake, but by ordinary choices in design and operation, repeated in mills from New Hampshire to Lancashire. Maintenance crews in the 19th century mills faced a puzzle with no good answers. Day after day, they inspected the massive flywheels and their engine rooms using the tools at hand, a careful eye, a hammer for ringing tests, and a sense of the machine's rhythm. But these methods could only reveal flaws on the surface. Internal cracks, those tiny fractures that grew with every revolution, remained invisible, buried deep inside the cast iron. Even the sharpest engineer, listening for a dull note or scanning the rim for hairline seams, had no way to spot the danger building within. The architecture of these mills only made things worse. Flywheels of 60 or even 100 tons spun in brick engine rooms, often sunk below ground level. The brick walls were built to carry the weight of the machinery above, not to contain a failure. There were no steel bands, blast-proof barriers, or reinforced pits. If a rim fractured, nothing in the design would stop fragments from tearing through the walls, floors, or even neighboring buildings. In some mills, engine rooms were wedged between workshops, offices, and storage areas, crowded spaces where workers passed within feet of the spinning mass. The geometry of the mill complex concentrated risk. Power radiated outward from the engine house, but so did the threat. A fragment launched at rim speed, 40, 50, even 100 miles an hour, could travel through brick, timber, and glass with barely any loss of momentum. There was no standard for containment, no routine for deep inspection, and no warning before catastrophe. The very design that made centralized power so efficient left entire factories exposed to a danger that could not be seen, measured, or managed by the maintenance crews who lived with it every day. In Pennsylvania, a winter night in 1916 brought the Montgomery power plant to a standstill when its main flywheel, running unseen below the engine room, fractured at speed. Fragments weighing more than 500 pounds shot through 2-foot-thick brick walls. One chunk landed over 100 yards from the plant. Another smashed through a tin shop and buried itself in a sandbank 600 yards away. The plant was ruined. Only the hour spared lives because most workers had already left for the night. Across the Atlantic, English mill towns recorded similar scenes. In Bradford, engineers found iron segments embedded in the walls of neighboring buildings. Some pieces traveled hundreds of feet, propelled with enough force to breach stone and timber. These were not isolated accidents, nor were they products of reckless operation. Engineering journals of the 1890s cataloged dozens of such failures, each one described in the language of fragments, wall breaches, and the sudden conversion of stored energy into destruction. The pattern was unmistakable. Wherever these massive wheels spun, whether in the textile mills of New England, the steelworks of Pennsylvania, or the factories of Lancashire, the aftermath of failure looked the same. Half-ton sections hurled from their pits, brickwork torn apart, and machinery left in ruins. Reports from insurers and technical societies read like accident logs, each entry a variation on the same theme: energy concentrated at the center of production, released in an instant with consequences far beyond the engine house walls. The evidence pointed not to a single flaw or a freak event, but to a systemic hazard built into the very logic of centralized steam power. When a cast iron flywheel fails, the stored energy doesn't fade away. It detonates in an instant, transforming each broken segment into shrapnel. The physics is unforgiving. At the moment of rupture, every pound of iron at the rim is moving at the wheel's full speed, and all that kinetic energy has to go somewhere. For a typical 30-foot wheel spinning at 60 revolutions per minute, the rim travels at over 100 miles per hour. If a 250-pound chunk breaks loose, it carries 16.7 megajoules of energy, enough to punch through brick walls, splinter beams, and keep going. A 1,000-pound fragment holds 4 times that, 67 megajoules, the energy of a small artillery shell. Fragments don't just drop, they launch tangentially, flung outward at the speed of the rim. In the Amos-Skeig disaster, pieces weighing up to half a ton, shot through 3-foot-thick brick, soared hundreds of feet across the Milliard, and even landed across the Merrimack River. The brick engine room, built to support machinery above, offered no resistance. Walls became little more than obstacles, breached in a fraction of a second. The numbers are stark. The energy released by a single large fragment rivals a truck crash at highway speed. There is no gradual failure, no warning pause. The wheel's stored energy is instantly converted to motion, and every loose segment becomes a projectile. This is why containment failed so completely. The forces at play simply overwhelmed anything not specifically engineered to resist them. In these moments, the flywheel's original purpose to stabilize and protect the factory reversed, turning it into the very source of destruction. Insurance companies, faced with mounting claims from flywheel disasters, began demanding changes that would at least limit the scale of destruction. Their ledgers showed a hard truth: repairing the aftermath of a burst wheel often cost more than the wheel itself. Some mills responded by building timber or steel housings around their flywheels. Test and real-world failures showed these barriers could stop fragments up to about 300 pounds, enough to catch small pieces, but not the half-ton chunks that sometimes broke loose. Others dug deeper pits beneath the engine room, hoping that if a rim failed, the earth would swallow the debris before it reached the factory walls. Speed limits became another tool. Insurers sometimes insisted that mills cut flywheel speeds by as much as 25%. This single change could halve the stress in the rim, since tension rose with the square of the speed. But every reduction in speed meant less power delivered to the machines above, and owners worried about falling behind competitors. Some engineers experimented with steel rims, which could stretch rather than shatter, absorbing impacts that would have split cast iron. Tests showed steel rims deformed under stress but rarely exploded, an improvement though at a higher cost and with new maintenance demands. These remedies were adopted unevenly. Every fix came with a trade-off: lower production, higher expenses, or new technical challenges. The economics of the mill often decided which risks were tolerated and which were addressed. For many, the cost of true containment or safer design was simply too high until disaster struck. Electrification swept through the mills in the early 20th century, bringing a solution that was as decisive as it was simple. Instead of relying on a single giant flywheel to smooth power for an entire factory, engineers began installing dozens, sometimes hundreds, of small electric motors, each dedicated to a single machine or a small group of machines. This shift didn't just change how power was delivered, it rewrote the entire risk equation inside industrial buildings. The effect was dramatic. At the Arkwright Mill in Fall River, Massachusetts, the conversion in 1914 eliminated the central flywheel and replaced it with a network of localized motors. The largest indoor rotating mass dropped by more than 90%, from tens of tons down to a few hundred pounds at most. Failures, when they happened, became contained events limited to a single machine rather than threatening the entire complex. Insurance records from the period show a sharp decline in catastrophic claims. Maintenance crews could now isolate problems, swap out motors, and restart production without risking a chain reaction of destruction. The new system also changed the economics of power. Instead of one engine house dictating the fate of every loom and lathe, factories gained flexibility. Output could be scaled by adding or removing motors as needed, and energy losses from long-line shafts and belt drives all but vanished. The logic of centralized mass, so attractive in the age of steam, faded into history. With electric motors, the hidden danger at the heart of the mill was finally diffused, replaced by a distributed network where risk was local, manageable, and above all, no longer explosive. The real hazard was never just faulty metal. It was the economic logic that valued centralized power over containment, underestimating both fatigue and the stored violence within spinning mass. Today, as grid-scale batteries and turbines multiply, the same physics still governs risk. Every design choice carries a hidden assumption. If you want to keep questioning what we build into our world, subscribe and join the investigation into the unseen costs of progress.